about the relationship between two variables called direct and indirect variation. I'm going to start with a scenario to kick us off. So if we're talking about finding area of a rectangle, you all know that is length times width. So let's say I'm giving that the width is 2. Let's complete this table. So for example, let's say we have a length of 1. Well, the area would be 2 times 1. That would be an area of 2. Let's pick another length. How about 2? 2 would give us an area of 4. 2 times 2 is 4. If we had a length of 3, 2 times 3 is 6, and so on. 4 times 2 is 8. You get the idea. Let's look at what this graph would look like if I was going to graph this. Length is my x-axis. Area is my y. And I've got 1, 2, 2, 4, 3, 6, and 4, 8. If I had plotted them more accurately, they would all fall on the line. So this is called a direct variation. And the reason why is because as the length increases, the area also increases. The more we increase the length, the more the area will increase. The formula for this would be area is the length times 2, because we held the width constant. Okay? When we have a direct variation, the default formula is y equals x times k, or usually they put the k first. K times x. K is the constant. That is what we're always multiplying by. In this case, it was 2. So whenever x is being multiplied by a constant number, you know you have a direct variation relationship. Okay, now I want to move on to how does that relate to an indirect variation. So, using this same scenario, I'm now going to hold constant the area. I'm telling you that this rectangle can only have an area of 12. So let's think of some possible lengths and widths. Well, if we have a length of 1, then my width is going to have to be 12. 1 times 12 is 12. If I have a length of 2, then my width would have to be 6 to keep my constant area of 12. If I have a length of 3, my width has to be 4, and so on. You get the idea. Okay, let's look at this graph to see how this one compares. So for this, I have length on my x-axis, and I have width on my y. So 1, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somewhere up here. 2, 6, somewhere in there. 3, 4, 4, 3, 6, 2. This graph kind of looks like that, okay? This is called an indirect variation. And you'll notice the difference that as the length increases, my width has to decrease. That is a characteristic of an indirect relationship. The formula that we would have is, in order to find our width, we would take our area and we would divide by the length. So the formula for indirect relationship is our constant is divided by our input. That is the formula. K is still our constant, just like indirect variation, but now is being divided by. Another way you could write this, you could also write this as, if I multiplied by k on both sides, you can also see it as x times y equals the constant. So that is another way of writing the exact same thing. All right, now that you have an idea of what direct and indirect variation is, we're going to focus on indirect variation and look at some scenarios. Just to sum up, direct variation is when something is increasing, the output is also increasing. Think about your paycheck. The more hours you work, the more your paycheck's going to be. because what's constant is how much you're paid per hour. If you make $5 an hour babysitting, you work more hours, your paycheck is going to go up. Okay? We're going to focus on indirect variation scenarios today. Okay, let's look at a scenario where inverse variation occurs. This scenario, it says the hours it takes for students to decorate the cafeteria for the homecoming dance varies inversely as the number of students. Last year, 30 students finished decorating the cafeteria in 8 hours. If only 24 students show up this year, how long will it take to decorate? So it went ahead and told us that we have an inverse relationship. So we know we're going to be using this formula right here that we established. So hours is going to be our output. That's going to be our y. All right. We don't know the constant. Constant in this scenario would be like how many work hours are needed to happen in order for the students to fully decorate the cafeteria for the homecoming dance. And then x is going to be the number of students. I'll label it as workers in this case. So this is like the total project divided by how many students we have will give us how many hours it's going to take them all to decorate for the dance. So the first scenario they gave us is last year 30 students finished decorating the cafeteria in 8 hours. If we can find out this relationship, then we'll be able to figure out how many work hours total were put in so we know what that constant of variation is. So in order to solve this, this is division. To undo division, you have to multiply. So I'm going to multiply by both sides. 8 times 30 is 240. So that's my constant of variation. Now we can look at our scenario. This year, they're only expecting 24 students to show up. So they want to know how long is it going to take to decorate the cafeteria. So we know there's 240 work hours that are needed. And maybe I'll label this as H because that's the hours that it's going to take. And here's our students. 24 students only showed up. So we can see that that means it's going to take 10 hours for them to decorate if only 24 students show up. So that's how an inverse variation relationship works. Be sure that you know how to not only write the equation and solve. Let's try another example. Assume that y varies inversely with x. They're giving us this formula right here by saying that. If y is 12, so let's plug in y is 12, when x is 4, find x when y is 6. So we first need to find our constant so that we can answer the second part of the question. So we will multiply by 4, telling us that our constant of variation is 48. So our formula is going to be that. Now we can use it to find x when y is 6. So I'm going to plug 6 in for y and solve for x. Be careful when you're solving for x here. I see a lot of people still trying to multiply, but notice that the 48 is on top. So you would multiply by x on both sides, then you would divide by 6. So x is going to be 8. 6 goes into 48 8 times. And that's all you would do. This question is asking if this table represents an inverse relationship. One thing we know about an inverse relationship is as x increases, y decreases. So that's one thing we can look at in our table. X is increasing here, is y decreasing? It's really not. So we can already tell at this point that it's not going to be an inverse relationship. But another way is to check and see if they have a constant value that they are, that a constant ratio that will come up. So for example, if you didn't see already that that was happening, you could plug in -7 here for x and -21 in for the y. And when you multiply both sides by -7, you could see that this is 147. And then you would try, so the constant between these two values is 147. Let's see if another one of these points gives us the same constant. So let's plug in 1 and 3. So if I plug in 3 for the y and 1 for the x, my constant is 3. We can see they do not have the same constant, which further confirms that this is not an inverse relationship. In order for this to be an inverse relationship, they would all have to come up with the exact same constant. So that's what you would look for if you're looking at a pattern of numbers, to see if they have the same constant value, which means they're an inverse relationship. So that kind of summarizes what we've learned so far for inverse relationships. Remember, for an inverse relationship, as the x value increases, the y value will always decrease at the same constant value.